Hello. We are continuing with our discussion on countability of sets. We have seen that a set capital A is said to be countable if the set of all natural numbers and capital A have the same cardinality. What is meant by saying that a set capital A and set of all natural numbers have the same cardinality? It simply means that we can define a 1 onto function from the set of all natural numbers to A. In that case, we say that capital A has the same cardinality as that of capital N. We have seen in one of our previous sessions that the set of all integers can be put into a one-to-one correspondence with the set of all natural numbers, and therefore the set of all integers is countable. And we have seen a few more examples of countable sets. In today's session, we are going to see that the set of all rational numbers is also, not very surprisingly, is countable. That means we can define a 1 onto function from the set of all natural numbers to the set of all rational numbers. We are going to see how can we define such a one-to-one correspondence and how to verify that it is actually going to be a one-to-one correspondence. We will also see the motivation behind defining such a one-to-one correspondence. Before discussing the issue related to countability of the set of all rationals, we will fix a set theoretical notation for Q. Usually we write Q as a set in this form. Q is the set of all real numbers that can be represented by the notation m by n, that's the ratio of integers, with m and n both integers and n not equal to 0. This is the standard set theoretical notation we usually use to describe Q as a subset of reals. Now, we have to discuss the countability of Q. That means that we have to probably establish a 1 onto function from natural numbers to the set of all rational numbers. But one most important thing while establishing a 1 onto function is that there should not be any duplication of elements in the set of all rationals. That means if you consider 1 by 2 is definitely a rational number appearing in this Q, but 1 by 2 actually appears more than once in the set Q as per this notation, because 1 by 2 and 2 by 4 they actually represent the same rational numbers, but they appear twice in this representation. So that is actually going to create some confusion for us, and therefore we will slightly modify the set theoretical description of Q in such a way that we won't be having any confusion regarding the representation of an element in Q. So we are trying to write down a new representation or a slightly different notation for set theoretical notation for Q in such a way that there won't be any confusion with this number will be appearing more than once, or this number will have more than one representation in the set of all rationals, etc., etc. So we will completely remove all these confusions by rewriting the set of all rationals in the following way. To avoid the confusion regarding representations of same number in different ways, like 1 by 2, 2 by 4, and then 3 by 6, etc. The possible confusion here is occurring basically because we are multiplying 1 by 2 with some number on the numerator and denominator, the same common number with numerator and on the numerator and denominator, and we are getting different notations. For example, 1 by 2 when multiplied with 2 on numerator and denominator, we will get 2 by 4, and 1 by 2 if we multiply with 3 and 3 on the numerator and denominator, we will get 3 by 6, etc. So to avoid this confusion, one possible strategy could be to just take the representation of a number provided m and n are in their lowest terms. Lowest term in the sense that GCD of m and n equal to 1. So 1 by 2, 2 by 4, all these things, everything will correspond to 1 m by n with m by n, m and n having no common factor other than 1. That means everything 2 by 4, 3 by 6, everything will be represented just by this number. So in this way we can avoid one confusion. So we can probably rewrite Q in the following way to avoid certain confusion. X real number, X is equal to M by N, not only that, with M and N integers, N not equal to 0 and GCD of Mn equal to 1. This is one possible way to avoid the confusion with 1 by 2, 2 by 4, 3 by 6, everything appearing in Q, same rational number with different notations. But still there can be some more confusion. For example, suppose that we are considering minus 1 by 2 and 1 by minus 2. Both these numbers 1 2 minus 1 2 and 1 minus 2 both have GCD, both satisfy the condition that the GCD of numerator and denominator has to be equal to 1. But these two numbers represent the same number once again. So still there is a confusion. To avoid all these confusions altogether, we are going to just rewrite in the following way. The set theoretical notation of Q we will modify further in this way. So X in R with X is equal to, we are going to altogether modify it. X is equal to P by Q, where P and Q are natural numbers, therefore both are positive natural numbers, and PQ they are in their lowest terms. But if you are writing like this, one possible problem here is that, not one possible problem, it is actually a problem. P and Q are natural numbers and therefore we are not considering 0 to be a member of this. To avoid this possibility, to avoid this confusion, we will include 0 separately, and that's it. This is the notation for Q we are going to use now. And we are trying to construct a 1 1 on 2 function from natural numbers to Q using this notation of Q as a set. To construct a 1 1 on 2 function from natural numbers to the set of all rationals, probably it is worthy to revisit what we exactly did for arguing that the set of what integers is countable. So we actually constructed a 1 1 on 2 function from set of all natural numbers to set of all integers using some special technique. What we precisely did is we arranged the integers in the following way. We took 0 as the first element, or singleton set 0 we took as one set. After that we took plus or minus 1 in another set. So the third set is then plus or minus 2, etc. So we splitted the set of all integers into smaller subsets, and the smaller subsets were in such a way that all these subsets were finite, and we arranged all these subsets. And then we assigned labels to each and every element in the finite subset, and we proceeded like that. Maybe we can follow exactly the same procedure for Q also, but the most difficult thing or most important thing is how can we split Q into finite subsets. That's what we are going to see now. So we are going to see first the procedure we followed for labeling elements in Z. So labeling in the sense that defining a 1 1 on 2 function from natural numbers to another set simply means that we are calling one of the elements to be the first element, or say x1. Second element, we mark some element as the second element and we call it as x2, etc. Therefore, basically we are labeling the elements using the notation x1, x2, etc. So how we did that in the case of set of all integers is what we are going to see now, so that we can probably get some hint about how to proceed in the case of set of all rational numbers. So the labeling was the following. The integers we divided like this: 0, singleton 0, union, then minus 1, then plus 1, and after that this is minus 2 and plus 2, etc. And maybe one more set, minus 3 and plus 3, union, etc. So that the total union of all these sets will be Z. This is a finite set, not that this is a finite set. This is a finite set, except the singleton 0. All other sets are having exactly 2 elements, but the important thing is they are all finite. After that, we assigned the labels like this. We labeled this one as the first element, or we may call this as x1. Now the label x2 was given to the least element in the set. x3 was given as a labeling for this element. So the numbers 2 and 3 we reserve for the second set. Proceeding like this, x4, x5 are these two elements, x6, x7 are these two elements, etc. We proceeded like this. So the basic technique is we splitted Z into finite sets, and after that we took the first finite set. Not only that, the technique is this: split Z into a union of finite sets. After that, arrange the finite sets in some particular order. Start labeling with the first set, label all elements in the first set, then go to the next set, label all elements in the next set, and proceed like that. This is the procedure we followed in the case of Z. So for labeling Z, what we did is write Z as a union of n 1 to infinity an, where each an finite. Not only that, each and every set in this particular breakup, they are all disjoint. ai intersection aj equal to empty set when I not equal to j. Different sets are disjoint. And one more thing is each an is finite. This is the property. This is the second property. Each an is finite. And the third thing is arrange. So of course, when we are arranging, when we say an, it means a1, a2, etc. Therefore, we have already arranged these subsets. So next step is label elements in a1, then in a2, etc. So since we know that Z is equal to union an, once we label all these an's, definitely every integer in Z also will be labeled. This is the procedure that we followed for labeling or defining a 1-1-2 function from natural numbers to Z. So we are trying to see if this is going to be possible for rationals also. See, how did we split this Z into smaller subsets can be observed by looking at these elements. Here we have plus or minus 1, and both these numbers have the same magnitude. Both these numbers have the same absolute value, which is 1. Next one, we have taken absolute value equal to 2. So our splitting of Z is in the following way: a1 having absolute value 0, a2 having absolute value, this is the absolute value of elements, a2 having absolute value 1, a3 having absolute value 2, etc. Now, since a1, a2, etc. are given absolute values as whole numbers, so absolute value of not exactly every element with absolute value with same absolute value put in same set. That is a strategy we followed. So since 0 is having the only one element with absolute value equal to 0, therefore that set is singleton. A2 is the set of all elements with absolute value 1, therefore plus 1 and minus 1 goes inside A2. A3, the set of all elements with set of all integers with absolute value equal to 2, therefore plus 2 and minus 2 goes inside that. And we splitted Z according to absolute values. So the important thing about absolute values of integers is that we will be actually getting the set of all whole numbers. So absolute values are of ANs are whole numbers, means numbers from 0, 1, 2, 3, etc. And therefore, since we know that the set of all whole numbers, this is actually it's a subset of, maybe we can say like that. It is not actually a subset, it is actually equal to the set of all whole numbers, because we are getting all the whole numbers 0, 1, 2, etc. But therefore the absolute values, it's a subset of whole numbers, therefore there is a least absolute value. Therefore there is a least absolute value. This is why? Because of well ordering principle, because we know that if we have a subset of the set of all whole numbers which is non-empty, then there is a least element in that. Okay, so the least absolute value, we know that it is 0, therefore that is 0. And after that we know that if we remove 0, then still we have absolute values, and therefore there is a least element in that set of absolute values which is 1. So we have 1, we have 2, etc. So the basic property that we use for arranging A1, A2, etc. is actually the well ordering principle. Least first, next least second, next least third, etc. That is a technique that we used. Now in the case of Q, this absolute value technique is not actually going to work, because in the case of Q, so suppose that we write this is 0. So definitely this is the 0 is the element with the least possible absolute value. That's for sure, no doubt. But after that, the question is, what is the next least? What is the next least absolute value for rationals? Now we are in trouble, because is it 1 by 2? Is it 1 by 3? Is it 1 by or 10 by 249? Some random number. So what is the least possible absolute value after 0? So if you try to divide Q based on absolute value, we are not going to reach anywhere. That's going to be a huge problem for us. We don't know what exactly is the next least. So we cannot arrange like that. So there is not actually a possibility for splitting Q into subsets. Maybe some other way we can try. Maybe we can write, suppose we are writing like this. A1 is equal to set of all rationals with the denominator, we know that, plus or minus P by Q. Suppose that we write plus or minus 1 by n, where n belongs to natural numbers. That means that, okay, this is maybe we should write before that A0 equal to or A1 equal to 0. Now A2, probably we can write everything with place 1 by n, that is plus or minus 1, plus or minus 1 by 2, plus or minus 1 by 3, etc. Now suppose that A3 we are writing everything with a denominator equal to 2. So plus or minus 1 by 2 is already taken. So we have to take 2 by 2, which is 1. Of course we have not taken 1. We have taken 1 also. 2 by 2 also we cannot take. 3 by 2, 4 by 2 is 2. That is not taken. Plus or minus 4 by 2, which is 2, etc. But now the problem here is that suppose that we label A1 with 1, this element with 1. Now suppose that we label this one with 2 and 3, we label plus or minus 2 with 4 and 5. Now the problem is that we are not going to finish the labeling inside A2 itself, because A2 itself is an infinite set. Therefore, we will be keeping on labeling elements in A2 itself without even looking at this A3. So how can we make sure that every element in Q will get a label? Because we are never going to come out of A2 after completing the labeling there. So that is not a possibility. So this is also not going to work for us. So definitely we need A1, A2, etc. as finite sets, and then only we can think about the strategy that we adopted in the case of the set of all rationals. Okay, now the problem is this. Just come back to the notation of Q. This is a set of all X and R. We are dropping that. We will simply write set of all P by Q instead of writing X in R, where X equal to P by Q, with P, Q, natural number and PQ GCD equal to 1 union 0. This is the notation we have. Now the question is to split Q into finite set based on some size of elements in rationals. See, in the case of integers, that size we chose for integers, size of an integer equal to absolute value of the integer. This is the convention that we used. But here we have to define a slightly different size. But because with size modulus of n, there are only two elements. What are the two elements? Plus n and minus n. And if n is equal to 0, there is one element. For each size, there are only finitely many. In fact, one or two elements. So now the question is, define a size for P by Q so that with maybe if we define a size for P by Q as a natural number, just like we define size of n to be modulus of n, size as a natural number in such a way that there are only finitely many P by Q with a particular size. So we have to define size is actually something that we are going to define. So this is size. This we are going to define. So this is something that we have to define. So we have to define size in such a way that size is going to be a natural number. Size must be a natural number. Not only that, once we define the size, there must be only finitely many elements with one particular size. For example, suppose that, and also we want the size to be a natural number so that we can easily arrange. If elements having size 1, elements having size 2, elements having size 3, we can keep on arrange elements like that. And since we want only finitely many elements with size 1, finitely many elements with size 2, it will be easy for us to arrange elements in that particular set, label elements in that particular set. So this is the question we have, how to do this. For P by Q, define a size. So there are, instead of, if there is only P, then plus or minus P we can take modulus. But here we have P by Q. So we have to take care of two numbers at a time, the number P and number Q. So one probable geometric intuition we can get from this idea. Suppose that we draw a rectangle with sides equal to P and Q. Suppose we do this. Suppose we are doing this. So this one is size P, this is a natural number, Q, this is a natural number. And now suppose that we have another rectangle, probably with sides equal to R and S. So we have to compare, we have to define size in such a way that we must be able to compare P by Q and R by S using some natural number. So P by Q has size this, R by S has size this. So size of P by Q is a natural number that is less than size of R by S, which is another natural number. So we can say that P by Q we will put first and R by S we will put later. So to define a size, if we consider the rectangle example, how do we compare these two rectangles? So we can compare these two rectangles probably using compare rectangles. So using area we can of course compare. Area is nothing but PQ or RS. or using perimeter we can compare. What is perimeter? 2 times P plus Q, 2 times R plus S. So what 2 times P plus Q comparing with the 2 times R plus S is nothing but comparing P plus Q with R plus S. We can compare these two rectangles using these numbers, and of course PQ we know that it's a natural number. RS we know that that's also a natural number. Just like that, P plus Q is a natural number, R plus S is a natural number. But P plus Q seems to be somewhat more easier for us because we don't have to multiply. You will get a smaller number, because if you are taking PQ, you may probably end up with a larger number. So we use P plus Q as our technique for comparing P by Q and R by S. So we are going to define size of P by Q equal to P plus Q, and size of minus P by Q we define as modulus of size of P by Q itself, and size of 0 we define it to be just equal to 0. So we have, so how do we make a comparison using this size? For example, 1 by 2 and 3 by 4. So size of 1 by 2 equal to 1 plus 2 equal to 3, and size of 3 by 4 equal to 3 plus 4 equal to 7. Therefore we say that 1 by 2 has less size. So this is so we will say that 1 by 2 has less size compared to 3 by 4. Therefore 1 by 2 will be appearing before 3 by 4. Now our main aim for while defining the size is to split Q based on this size. So we got size as a natural number. Now we are going to split Q in the following way. So we are going to split Q in this way. Take A1 equal to singleton 0, the first element. Now take A2 equal to elements P by Q in Q with size equal to 2. So what are the elements then? P by Q with size 2 means that it is going to be 1 by 1, that's it. So minus 1 by 1 plus 1 by 1. So elements having same size, we will put the negative number first and the positive number later. So A2 is just this. Now what is A3? A3 is elements P by Q plus or minus P by Q with size equal to 3. That is equal to, what are the elements? Size equal to 3 means that 1, 2 can be there, plus 1 by 2 can be there. Next is 2 by 3, 2 by 1 minus plus 2 by 1. Okay, so these are the elements having size equal to 3. So there are 4 elements. So in general, AN is equal to plus or minus P by Q with PQ in N. GCD of PQ is equal to 1. Not only that, P plus Q equal to N. This is what our AN is. So we have defined A0, A1, A2, A3, etc. We can continue like this. So each and every rational number will definitely have a size. Therefore, each and every rational number will belong to one of these ANs. So it's clearly, every rational number will be definitely having a size, and therefore we can say that Q is equal to union n equal to n from 1 to infinity an. That's for sure, because whatever rational number we take, that's in the form p by q, and p by q, p plus q is definitely there. P by q will definitely belong to a p plus q. This is because p by q will belong to a p plus q. Therefore q is going to be equal to union this. And what about the disjoint nature of AI and AJ? Is AI intersection AJ equal to 5? See, if some element has to appear in AI, it means that p by q must satisfy p plus q is equal to I. But that p by q cannot actually satisfy p plus q is equal to j. If not, p by q belongs to AI intersection AJ implies p plus q is equal to I and p plus q equal to j. This is not possible because p plus q is equal to I and j. P plus q, p and q are elements with common ratio equal to 1. Therefore, if you are taking elements with common ratio equal to 1, there is no possible further cancellations. So p plus q will be equal to 1 and p plus q will be equal to j, and I and j, two different numbers, is not possible. This is not possible. Therefore, AI intersection AJ is empty. So Q is the disjoint union of elements. So Q will be equal to A1, that is singleton 0, A2, that is, we have seen, minus 1 by 1, 1 by 1, A3, that is minus 1 by 2, 1 by 2, minus 2 by 1, which is minus 2, minus 2 by 1. This is A3. And if you want to write A4 also, probably we can write even that. A4 is, so we need minus 1 by 3, 1 by 3. So we are starting with the least numerator. And numerator increasing in A from left to right. See here, 1, 1, 2, 2. Numerator is increasing, whereas denominator is decreasing. 2, 2, 1, 1. So minus 1 by 3, 1 by 3. Next is minus 2 by 2, but minus 2 by 2 is 1. That's minus 2. Not only that, we have to choose p by q in such a way that GCD of p and q is 1. So minus 2 by 2 we cannot take. The next number is going to be minus 3 by 3. Minus 3 by 1 and 3 by 1. No, minus not here. Minus of 3 by here we have to write minus of 1 by minus 1 by 3. So that's it. These are the elements in A4. So how many elements will be there in AN maximum? So AN will be having elements of the form p plus q equal to n. So p plus q is equal to n is possible in and what are the possible ways of getting p plus q is equal to n? What are the possibilities for p and q? Both are natural numbers. So 1 plus n minus 1 equal to n, 2 plus n minus 2 equal to n, etc. If we come down like this, n minus 1 plus 1 equal to n. So there are n minus 1 possibilities for p plus q equal to n. But if we consider plus p plus q, p by q, and minus p by q, then there are 2 times n minus 1 possibilities. So an will be having at most 2 times n minus 1 elements. Therefore, an has at most 2 times n minus 1 elements. So why we are saying that at most 2 times n minus 1 elements? Because see, if we are getting p plus q is equal to n, that is not enough for including p by q in an. GCD of pq also must be equal to 1. So for example, suppose that we are having 4, 2 plus 2 is equal to 4, but that 2 by 2 is not included in an. Therefore, we can say that there are at most 2 times n minus 1 possible elements in an. So we cannot say exactly 2 times n minus 1 elements, at most 2 times n minus 1 elements, where n is starting from a2, n is greater than or equal to 2, because a1 is having just one element, and this is for a1 has only one element. Now, this is the way in which we are writing this ans. Now, how do we give labels? So we are going to give labels for all these ans, all the elements in this an. So our labeling is the following. So give 0, label 1. We have arranged a2 in such a way that the numerator starting element has a numerator the least and it is negative. So this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. So we splitted Q into finite sets, A0, A1, A2, A3, etc. All these finite sets are arranged in the increasing order of the size. The size of A1 is just 0. Every element has size 0. Every element in A2 has size 2. Or this is not actually size 0. This we want, if we want, we can say that okay, we define to have size 0. Every element here has size 2. Every element here have size equal to 3. Here A4 size equal to 4, etc. We splitted Q according to size. Each and every size corresponds to finitely many elements. So we are having only finitely many elements in each and every an. Gave labels to elements in A1, A2, A3, etc. This is how we are proceeding. So we have finally achieved a labeling for the set of all elements in Q using the newly defined size. Okay. Now there are a few questions that we have to answer. So we have defined a one-on correspondence. We have defined a correspondence from natural numbers to rational numbers. The questions we have are the following. So question 1. Will every natural number be used for labeling rationals? So that means that can it happen that the number 10,000 will not be having any, the natural number 10,000 will not be having any rational number as its image. So precisely, basically what we are saying is, if f is the labeling function from natural numbers to rational numbers, can we say that the number 10,000 also will be having an image in the set of all rationals? That is, will every n in n get an image. See, it is necessary for a mapping from or a correspondence from natural numbers to rational numbers to be called as a function. We must make sure that every element, every natural number gets an image. So how can we make sure that every natural number will definitely get an image? We will consider the following example. Suppose n is equal to 10,000. But 10,000 is nothing but it's a rational number, 10,000 by 1. Therefore, it belongs to A 10,000 and 1, because this is P and this is Q. GCD is equal to 1. Therefore, it belongs to A 10,001. P plus Q is equal to 10,001. Therefore, this belongs to A 10,001. Now, we know that each AN is non-empty. Why so? Because n minus 1 by 1 belongs to AN. Because n minus 1 by 1 plus 1 is equal to n, and this belongs to AN. So each AN is non-empty. Each AN will use at least one natural number for labeling. Each AN consists of at least one element. Each AN will use at least one natural number for labeling. Therefore, by reaching A 10,001 or by reaching A 10,000, 1,000 numbers from n will be used for labeling. Therefore, before reaching A 10,000, before reaching A 10,001, each and every AN will utilize at least one natural number for labeling, and therefore we can make sure that by A 10,000 itself, the number 10,000 would have been already used for labeling. Therefore, what we said here can be answered as yes. So we have the next question. Will any n in n be used for labeling two rational numbers, two or more? This is the next question we have. Will any natural number be used for labeling two or more rationals? Or in other words, what we are asking here is, suppose that we are choosing again 10,000. So will it happen that 10,000 is used for labeling one P by Q, and the same 10,000 is used for labeling another R by S? Is that possible? That's the question that we are asking. This is not actually possible, because if we use 10,000 for labeling P by Q, say, then P plus Q is going to be equal to some number, and after labeling this P plus Q, and definitely P plus Q is going to be some natural number and R plus S is some natural number. So assume that P plus Q is less than R plus S. So if we use this 10,000 for labeling P by Q, for labeling the next number R by S, which is having more size, we will be using 10,001 or more. So this can be seen the following way. Let P by Q R by S be such that P by Q P plus Q less than R plus S. So if N is used to label P by Q, then only N plus 1 or more will be used for labeling R by S. Therefore, this N cannot be used for labeling P by Q and R by S. Now, if P by Q is P plus Q is equal to R plus S, what will happen? If P plus Q equal to R plus S, then they are in the same, equal to say some M, then P by Q and R by S both belongs to AM. But in that case, P by Q and R by S belongs to AM. In that case, either P by Q comes, either this P is less than R or R is less than P. But then suppose that P is less than R, then N will be for P by Q, N plus 1 or more for again R by S. So this is the case here when P by Q and R by S belongs to the same AM. But now there is one more possibility about which you have to probably think, that P by Q and P is equal to R. But in that case, P by Q is going to be a positive number and R by S is going to be a negative number. So if P by Q is a positive number and R by S is negative, R by S will be given the N and P by Q will be given N plus 1. Or if R by S is negative, R by S will be appearing before P by Q. Therefore, if N is going to be used for P by Q, that means that N minus 1 or something less than that will be used for labeling R by S. Therefore, the answer here is no. One particular natural number will not be used for labeling more than one rational number. So question 1 and 2, the answers together imply that the correspondence that we have defined is actually a function. Now questions 1 and 2 says that the labeling we defined a function. Now what is the next question remaining? So is it 1 1? So what is going to be asking if this 1 1? The question is, what we are precisely asking is it possible that one single rational number will get two labels? That is it possible that a single P by Q gets two labels? So in the function language, that means f of n equal to P by Q equal to f of m for m not equal to n. Is this possible? That's the question we are asking. for if this function is 1 1. This is not actually possible because by the construction itself we are actually starting from one rational number in an and then we are finding out the labels. Or in other words, suppose that we are using n for labeling one p by q. After that p by q is never appearing later. So the next number will be used for either minus p by q, or the next number will be used for p plus 1 by q minus 1. So in this case also the natural number m will be used for labeling some other rational numbers. So this answer, we can see that the answer is yes. Now the last question is this und. So to see this, suppose that a p by q belongs to an. So for labeling all rationals from a1 to an, how many labels are actually required? So one label for a0, this is a1, one label. Next is if you go back, we can see that next one is minus 1 plus 1, therefore there are 2. We have seen that after that it's going to be this is 2 times 1, 2 times 2 minus 1. We'll write that 2 times 2 minus 1 at most. A2, 2 times 3 minus 1 up to a3 plus etc. or up to an 2 times n minus 1. Labels are sufficient for labeling all rationals up to in an. Therefore, this number is actually a finite number. 1 plus 2 into 2 minus 1 plus 2 into 3 minus 1 plus etc. 2 into n minus 1. We don't actually require these many integers, these many natural numbers, something less than that. But these many natural numbers are definitely there because the number of natural numbers is infinite, number of labels are infinite, and for labeling up to an, we require only these many natural numbers. Therefore, definitely every element in an also will get a label. Therefore, this p by q also will get a label. Therefore, p by q also will get a label. So the labeling we defined says that the labeling we defined is a 1 onto function from n to q over the cardinality of n and q are exactly the same. Therefore, q is countable. This is what we have established. It's quite a long proof, but actually the proof is not very long. We try to make it somewhat simpler, and we try to present it in such a way that we can imitate what we exactly did in the case of set of integers. That's why the proof looks to be somewhat long, but if you carefully look at what we have done, the proof is quite short, and the explanation is actually much more. Okay, I hope that you can understand this proof, you could understand this proof, and probably just go through that. Try to see the image of a few rational numbers, try to see the label of some rational numbers, and you will see that this actually works. We'll stop here. Thank you.